Okay, all right. Now we're gonna summarize how we compare acidity of an acid. All right. So when you get a bunch of acid and you have to compare their acidity, first off, if you know the pKa value, go with the pKa value because pKa is an experimental value. It's real. Use that first. All right. But most of the time, pKa value. I mean, it's just so difficult to take all the acid in this world and measure the pKa value. I mean, it's impossible. So we have the OREO, those factors we just learned, the textbook called OREO. We have atom, resonance, induction, and orbital, right? Atom size and electronegativity. So these 5 factors use OREO to help you determine who's stronger, who's weaker acid. Okay, it's just a prediction, not always true. It's not always true. I'll give you some example that's not true. For example, in this case, if this carbon were to be a negative charge, the conjugate base, all right, this amino group, nitrogen got a negative charge on it. Well, nitrogen, the electronegativity is much higher than the carbon. So this guy is supposed to be a stronger acid. But in this case, orbital effect outweighs the atomic effect, the electronegativity of the nitrogen. Okay, in this case, it doesn't work there. And another one here. All right, this guy, if you got a negative charge here, the conjugate base, and the negative charge here, the conjugate base. This guy have a resonance. You can do resonance structure there, all right? So it is an allylic position. But somehow, again, hybridization or orbital effect outweigh the resonance effect. It doesn't work, okay? And another example, this one, OREO works. We know the pKa value of amino group amine. But we don't have the pKa value of this guy and that guy, right? But using an OREO, this guy have resonance. If you have negative charge here, this guy have resonance. This guy, a negative charge here, you have just an inductive effect. Get that? So and resonance usually much better than inductive effect. But this guy doesn't have anything stabilize the negative charge on this nitrogen. We can use OREO to predict the pKa of an unknown acid. All right. Anyway, my point is, if you know the pKa value, use the pKa value first. If you don't know it, in this case, use OREO, size, En, resonance, induction, orbital to help you predict the acidity of an acid. Okay. All right, we're gonna do this together here. So do it by yourself first. Just try to think, all right, and then compare with me. How do you think about it? In A, all right. So if you make this oxygen here become a conjugate base, same thing on this side, right? The negative charge is going to be on oxygen. So size, electronegativity doesn't matter. They are the same, oxygen and oxygen. Okay. Resonance, negative charge here. This is allylic position. You can go up to here. This guy can do the same thing. Negative charge here. Put it down here and you flip the double bond up to the oxygen. Do negative charge there. They have the same resonance form. It doesn't work. But what works in this case is the inductive effect of fluorine, right? So fluorine help stabilize the negative charge on oxygen, and this 2-fluorine is closer to this oxygen than the other oxygen. All right. So because of induction, H right here on the left side is more acidic. All right. Now in the case of B, I'm sure you can see it right now. Alkyne, alkene, and alkane, totally alkyne. Right, because of the orbital effect. Well, but if you think about it, if you have a negative charge here on carbon and on this carbon and carbon, same En, same size, doesn't, so they don't do anything there. None of them have resonance effect. Okay, inductive effect. What? No electronegative atom nearby, so can't use that either. The only difference is this carbon and sp orbital. The negative charge on this carbon is going to be closer to the nucleus of this carbon and stabilize this, the negative charge more than an sp2 carbon can. Okay, so orbital effect there. All right, now in C, what's going on there? H1 or H2? And H2, not sure you can see it. All right, I'm going to show you here. There's a resonance effect here. All right, so if you don't get it, draw out the resonance form. Okay, so in H1, that's a resonance form. Right, and you can draw a resonance from there. No, I said it wrong. Hold on. Draw out the conjugate base. Good. And there's no resonance form for this conjugate base. You can do on the left, can do on the right. You over octet these 2 carbon. Right. But if you do draw out the conjugate base of H2, On the left side, you can't do on the left side, but you can do on the right side. There's a resonance form there, right? So H2 is this negative charge is more stable. It's more stable. So H2 is more acidic. Okay. All right. Next one, D. I'm not sure you can see the resonance there, but all right. All right. Draw out the conjugate base first. Okay. So H1 look like that. Does it have resonance? Yeah, right there. That's a resonance. This allylic position. Double bond here. There's an allylic position. Now, for H2, there's no the conjugate base doesn't have resonance form. So no, more resonance form, more stable, and H1 is more acidic. All right. Lastly, E. Can you see it? Let's start with drawing the conjugate base. All right. For H1, look like that. What do they have here? Negative charge on carbon, and they got resonance form. Good. That's even better. All right. Now, in the case of H2, the negative charge on that oxygen, all right? It also got one resonance form. Oh, what's the tiebreaker? Well, we don't even need to go to resonance form. Look at it right here. Negative charge on carbon and oxygen, the carbon and oxygen. Negative charge on oxygen and oxygen. They have the same sign, of course, but oxygen and oxygen, much higher electronegativity than carbon, right? So, the electronegativity, so oxygen is higher, stabilize the negative charge better, right? So this negative charge gonna be happier than this negative charge down here, right? Which means that H2 gonna be more acidic. So pKa 5, this guy pKa about 20. All right. If you know the pKa value, you don't even have to do this, right? But sometimes OREO helps. All right. All right. We have class activity 3, question 1, 2, 3. This helps you reinforce the how to use OREO and the pKa table. Okay. And question 4, question 5. I have what's that? Keys down here. I use it wisely. Think first. Don't just look at the key right away. All right. Okay. A little segment. So we have Sheldon Cooper, Fun with Flag. Anyone here watch The Big Bang Theory? If you haven't watched The Big Bang Theory, well, how to explain this? It's just a bunch of scientists, really nerdy, and try to date a hot girl, and successfully he did. And anyway, so it is one of the characters there, and he is super nerd, got a PhD, work at as a professor, postdoc, a scientist at California Tech, was it Caltech? Something like the California Technology University. I don't know how it's supposed to phone it. Anyway, so he's a super smart, but he also have like a fun part. He called Sheldon Cooper Fun with Flags, put on YouTube, and it talk about interesting fact about flags. Okay, and I have this for you. Hold on, 1, 2, go. Okay, here's the flag of Norway. Do you know that they have 1, 2, 3, 4, 5, 6, 7 flags in the Norway flags? Right? We have Indonesia in here. We have Poland, which is reversed basically. We have Finland in the middle, France, Netherlands, and we have Thailand. That's very interesting. One flag got 7 flags in it. This is Norway, I think. All right. And speaking of Indonesia and Poland, it's switched. So we have red and white, and we have white and red for Poland. Right? Oh, take a look here. So Poland, white and red. Indonesia, red and white. And these two countries have a word tak. In Polish, it means yes. In Indonesian, means no. I don't know if it's a coincidence or not, but that's very interesting. Okay. All right, we go to the last video. Next one. Let's go.